In 1973, Fisher-Black and Myron shows published one of the most consequential results in modern finance. Today, we derive their formula from first principles. We begin with a model for how stock prices move. The stock price S follows geometric Brownian motion, a deterministic drift term, mu s dt, plus a random shock term, sigma s w sub t, driven by a Wiener process. Now suppose V is the price of a derivative, say a call option. Since V depends on S, which is stochastic, we need Ito's lemma to find how V itself evolves. Now, Ito calculus gives us three rules for simplifying stochastic differentials. These collapse delta S squared down to sigma squared S squared dot. Substituting back, we get the complete stochastic differential for V, a deterministic part and a stochastic part. The key insight, we can hedge away all randomness, form a portfolio pie holding the option and short delta shares of stock. The change in the portfolio mixes the random terms from dV and ds. If we set delta equal to the option's delta, the partial derivative of V with respect to S, the dW sub t terms cancel exactly. What remains is purely deterministic. A riskless portfolio must earn exactly the risk-free rate. Any deviation would create an arbitrage opportunity. Setting our two expressions for dpi equal and rearranging, we arrive at the Black-Scholes partial differential equation. Every European derivative satisfies this PDE, regardless of the drift mu, of which vanishes completely under no arbitrage. The Black-Scholes PDE looks formidable, but a clever substitution tames it. We remap stock price, time, and option value into new coordinates. The constants alpha and beta are chosen to absorb the drift and discounting terms. After substitution, the Black-Scholes PDE reduces exactly to the heat equation, though one of the most well-studied PDEs in physics. The initial condition encodes the call option's payoff at expiry. The heat equation is solved by convolution with a Gaussian kernel. We evaluate the convolution integral by completing the square in the exponent. The integral resolves into the standard normal CDFN. Two key quantities emerge, d1 and d2. And here is the cumulative distribution function of the standard normal, the area under the bell curve up to x. And here it is, the price of a European call option, with d1 and d2 encoding the moneyness, time, volatility, and the risk-free rate. Intuitively, the formula is just a present value calculation. What you expect to receive in stock minus what you expect to pay as the strike, each weighted by the probability that the option expires.